Okay, let's unpack this. I want you to picture driving a car, a really nice modern one. You get in, you punch in the GPS coordinates, you put it in drive, and the car, well, it basically does the rest.
Right. Lane assist, automatic gear shifts, all of it.
It's easy. It's adaptive. But then,
Yeah.
then you have the manual transmission, the stick shift.
The enthusiast's choice. Or, the control freak's choice, depending on how you look at it.
Exactly. It requires attention. It requires you to know exactly what the engine is doing at, say, 5,000 RPM. But the control, the precision,
Oh, it's unmatched.
you decide exactly when to shift. You aren't a passenger. You are the pilot. And today, we are popping the hood on the network engineering equivalent of driving a stick. We are talking about static routing.
It is a perfect analogy because in a world where everything is moving toward automation, software-defined networking, AI-driven traffic shaping, all of it.
Yeah, protocols that think for themselves.
Right. There is still this massive critical need for the network engineer to manually type in a route and say, packet, you are going this way and no other way.
And for this deep dive, we're digging into the Modern Technical Field Guide on IPv4 and IPv6 configuration. And I have to say, looking at the source material, this isn't just theory.
No, it gets pretty nitty-gritty.
It really does. It covers everything from the basic concept right down to the syntax you'd type into a Cisco router.
And the mission here is really to understand the why. Why, if we have dynamic protocols that can learn routes automatically, which sounds way easier.
It's a lot easier.
Would anyone want to hand-type destination addresses? It comes down to that balance between, manual and precise versus automatic and adaptive, and honestly, it comes down to certainty.
So let's set up the battle then. The guide frames this as a prize fight. In one corner, we have dynamic routing. In the other, static routing. How do you define the contenders?
Well, dynamic routing, so protocols like OSPF, EIGRP, BGP, think of that as your chatty neighbor.
Okay.
These routers, they talk to each other constantly. They gossip, hey, I know how to get to the 10.0.0 network, or, oh no, that cable just broke, let me find a new path. They share that info automatically.
So it's adaptive. If the road is closed, the GPS just finds a new route.
Exactly. It scales beautifully. You add a new router, they all shake hands, the map updates. But, and the source material is very specific about this, that chatter comes at a significant cost.
The resource tax.
Right. Dynamic protocols are resource hungry. They use a lot of CPU because they are constantly running complex algorithms to calculate paths. They use a lot of RAM to store these massive topology tables.
And bandwidth too, right?
Yeah, they eat up bandwidth because they are constantly shouting updates across the wires.
And then there's our hero for today, static routing.
The strong, silent type. Static routing is the administrator acting as a dictator. You explicitly tell the router, to get to network A, go through interface B. End of discussion.
The router doesn't think.
It just obeys.
And the stats on the scorecard here are really interesting. The source notes that static routing uses, low CPU and RAM?
Almost negligible. I mean, there's no algorithm running constantly to calculate the best path. You told it the path. It's like writing instructions on a Post-it note versus running a complex navigation computer.
And here's a stat that jumped out at me. 0 bandwidth usage.
Right. Dynamic protocols are constantly broadcasting or multicasting updates. I'm here, I'm here. Static routes? Silence.
They don't advertise.
They don't advertise themselves over the network, which actually brings us to a huge point that I think gets overlooked. Security.
Because nobody knows the route even exists unless they try to use it.
Exactly. It's the need-to-know principle. If you run a dynamic protocol, you are essentially broadcasting your network topology to every other device on the link.
Here's my floor plan.
Here are all my subnets. Here is exactly how my network is built. With static routing, you aren't broadcasting anything. It's stealthy.
So, okay, it's precise, it's secure, it's lightweight, it sounds perfect. So why aren't we using it for the whole internet? Why isn't Google just one giant static route map?
Because you would never sleep again. It's the manual part of that manual transmission. Imagine you manage a network with 50 routers. If you add just one new subnet, one new department in the building, you have to log into every single one of those 50 routers and manually type in the new route.
And if I make a typo on router 47?
You break the chain, the packet gets dropped. And troubleshooting is a nightmare because the network doesn't heal itself. If a cable cuts, a static route doesn't look for a backup path unless you've pre-programmed one.
It just fails.
It just fails. So it's high maintenance. It does not scale for the core of a large network.
So where is the sweet spot? The source material mentions something called a stub network. That sounds a little insulting to the network. You're just a stub.
It's not an insult, it's a topological term. A stub network is a network with only one path in and one path out.
A cul-de-sac.
Exactly, like a cul-de-sac or a dead-end street. If you live at the end of a cul-de-sac, you don't need a GPS to tell you how to leave your house. There's only one way to go.
Right, you just drive to the main road. That's it.
Exactly. So for a stub network, like a branch office connected to headquarters by a single fiber line, you don't need a complex dynamic protocol eating up CPU cycles just to figure out, go that way.
You just tell it where to go.
You just drop in a static route. It's the ideal use case.
Okay, so we know when to use it. Now let's get into the how. This is the mechanics section. The source calls this next hop mechanics. 3 ways to point a packet. And this is where I think people get tripped up.
They do, because they assume a route is a route.
And it isn't.
It definitely isn't. Once the router decides it needs to forward a packet, it has to know exactly what to do with it physically. And there are 3 distinct ways to configure that, and if you choose the wrong one for your cable type, you can actually crash your network segment.
Okay, let's start with the safe bet. Method number 1. The next hop IP, also called a recursive lookup.
Right. This is the standard best practice for any Ethernet network. Let's say router 1 wants to send data to router 2. In the configuration, you tell router 1, to get to the destination, send the packet to router 2's IP address, say 172.16.2.2.
That seems pretty straightforward. Why is it called recursive?
Because the router has to do double the work. It looks at the route and sees, go to 172.16.2.2. But then it has to ask, okay, but how do I physically reach that IP?
Ah, so it has to look at its routing table again.
Exactly. To find the interface that's connected to the 172.1c.2.2 network, it resolves the IP to an exit interface.
It looks at the map, gets a clue, and then looks at the map again to resolve the clue.
Perfect analogy. And on Ethernet, this is necessary. Because Ethernet is a multi-access network, there could be 10 routers on that one wire. You have to specify which device gets the packet by its IP so the router can resolve its specific MC address.
Okay, that makes sense. Now let's talk about the danger zone. Method number 2, the exit interface only. This one is labeled directly connected.
This comes with a giant warning label in the source material, and for good reason.
Yeah, it says restriction. Use only on point-to-point serial interfaces. But explain why. What happens if I use this on Ethernet?
Okay, let's break it down. In this method, instead of giving the next hop IP, you just say, push this packet out of serial port 0100. You don't care who's on the other side.
Because there's only one place it can go.
On a serial cable, which is like a pipe, this is fine. If you shove a tennis ball on one end, it has to come out the other.
Right.
But Ethernet is a broadcast medium. If you configure a static route on an Ethernet port that just says exit gigabit 01 without a specific target IP, the router assumes that every single host in that destination network is directly connected to that wire.
Wait, so if I point a route for the whole internet out of an Ethernet port like that?
The router assumes the entire internet is sitting on that one Ethernet cable.
Oh, wow.
So if a user tries to go to Google, the router shouts out an ARP request, who has Google's IP? If they go to Amazon, who has Amazon's IP?
It's ARPing for everything.
For every single destination users are trying to reach. It's called excessive ARP requests, or an ARP storm. It ruins performance, fills up the ARP table with garbage, and can just crush the CPU on the upstream router. It turns your network into a chaotic shouting match.
So the rule is absolute. Exit interfaces for serial cables only, never Ethernet.
Never Ethernet. Not unless you enjoy debugging slow networks on a Friday night.
Got it. Which leads us to method number 3. Fully specified routes. This sounds like the strict precision option.
It is. This is where you specify both. You tell the router, exit out of Gigabyte Ethernet 01 and send it to next hop IP 172.1t.2.2.
Why would you need to be that specific? It feels like wearing a belt and suspenders.
Well, it removes that recursive lookup, so it's a bit faster.
Right.
But it also avoids the ARP chaos we just talked about.
Okay.
It's also required in certain scenarios where there might be ambiguity. You know, if you have a switch connecting 4 different routers, you need to be fully specific to ensure the packet goes to the right neighbor.
Okay, let's look at the actual syntax. We are at the command line, router config, hashtag. What are we actually typing?
The command anatomy is pretty logical. It's IP route, then the network address you want to reach, the subnet mask for that network, and then, like we just discussed, either the IP address of the next hop or the exit interface.
And there's a little note here about IPv6 that seems like a classic
It's a
Gotcha.
very important prerequisite, yeah. By default, Cisco routers often have IPv6 forwarding disabled.
Oh, really?
Yeah, they're ready to be IPv6 hosts, but not routers. So before you can enter any IPv6 static routes, you have to type IPv6 unicast routing in the global configuration.
And if you forget that?
You can type routes all day long, but the router won't forward a single packet. It just sits there.
That is frustrating. Okay, so we've typed it in. How do we check our work? We need to read the map.
The golden command .show IP route. This displays the routing table. You're looking for the cat S on the far left. S stands for static.
And next to that, there are usually some numbers in brackets, like 10. The text calls this the trust score.
Technically, it's called administrative distance, or AD. This is vital to understanding how a router thinks. The router might learn a path to a network from 3 different sources: OSPF, EIGRP, a static route. It has to decide who to believe.
And it believes the lowest number.
Right. In routing, like in golf, a low score is better. A directly connected interface has an AD of 0, that's absolute truth. A static route has an AD of 1. A dynamic protocol like OSPF is way up at 110.
So if a router learns a path via OSPF with a score of 110, but I manually type a static route to the same place,
The static route wins.
with its score of 1.
Yep. The router ignores OSPF because the administrator is trusted more than the protocol. It's that administrator knows best philosophy again.
I like that. Now, we have to talk about some of these special routes. The source material gives us 2 cool concepts, the funnel and the sniper. Let's start with the funnel.
The funnel is your default route. You might also know it as the gateway of last resort.
A quad 0.
0.0.0 with a mask of 0.0.00, or in IPv6, it's 0.0.
So what's the logic there?
The logic is, I don't know where this packet goes. It doesn't match any of my specific routes for the branch office or the data center, so I'm just going to send it to the internet service provider.
It just catches everything.
It matches packets that do not match any other specific route. It's the catch-all. Without this, your router would drop any traffic destined for the internet because it can't possibly hold a routing table of the entire internet. That's, what, over 900,000 routes now?
So instead of memorizing the whole phone book, it just memorizes one rule. Send everything else upstream.
Exactly.
Okay, now on the complete opposite end of the spectrum, we have the sniper, the host right.
This is targeting with extreme precision. We're talking about routing to a specific 32-bit address in IPv4 or a 128-bit address in IPv6.
So not a whole street, but a specific house number.
Correct. The subnet mask is 255.255.255.255. It matches all the bits.
Why would you ever want to do that? Why not just route to the whole subnet?
Security and troubleshooting, mainly. Let's say you have an HR server or a payroll server with sensitive data. You don't want to open a route to that whole subnet for everyone. You want to create a path only to that specific machine, or maybe for management traffic. It lets you sniper shot a packet to a single destination without exposing the surroundings.
Sniper shot. I like that imagery. Okay, I want to move to one of the coolest concepts in this deep dive. The text calls it the spare tire.
Floating static routes. This is where we get to feel like magicians.
How does a row float?
It's all about redundancy. We talked about administrative distance, that trust score.
80.
By default, a static route is 81, but you can change that number.
Okay, so walk me through the scenario.
Imagine you have a primary fiber optic link to the internet. You configure a static route for it with a default AD of 1. The router loves it, puts it right in the routing table.
Great, traffic is flowing fast.
But fiber gets cut. Backhoes are the natural enemy of network engineers. So you have a backup link, maybe a slower 5G connection or a copper line. You want to use that only if the fiber breaks.
So I configure a second route for that backup link.
Yes, but here's the trick. If you just configure it normally, the router sees 2 equal routes and might try to load balance. You don't want half your traffic on the slow link.
Yeah, definitely not.
So you configure the backup route with an AD of, say, 5.
So it's less trusted than the fiber link, which is AD1.
Exactly.
Right.
And because the router trusts the AD1 route more, it completely ignores the AD5 route. It doesn't even put it in the routing table.
So it's just hidden.
It stays hidden. It floats in the background, invisible, waiting for its moment.
And the moment is when the fiber link goes down.
The moment that primary link goes down, the router says, oh no, the AD1 route is gone. It looks around, sees the 85 route waiting, and immediately installs it into the table. Traffic keeps flowing.
And when the fiber gets fixed,
The AD1 route comes back. The router sees it, has a better trust score, 1 is better than 5, and it kicks the 85 route back into the shadows. It's automatic failover using nothing but static logic.
That is incredibly clever. It's like having a spare key under the mat that only physically appears when you lose your main keys.
A perfect description. It's so elegant in its simplicity.
Before we wrap up, we have to address the IPv6 curveball. The source calls this the link local nuance.
Ah, yes, the FE80 problem.
So link local addresses, they're the ones that start with FE80. They are everywhere in IPv6.
They are, and that's the problem. FE80 addresses are not globally unique. They're only unique on that specific wire.
The text uses a great analogy here. It compares it to having multiple friends named Mike.
Right. Imagine router A is connected to router B on its left and router C on its right. Both router B and router C might automatically assign themselves the same link local address, say FE80.1.
So router A sees Mike on the left and Mike on the right.
Exactly. So if you just go into router A and type static route, send packet to FE80.1, the router freaks out. It asks, which Mike? The one on serial 0 or the one on gigabit 01? It's ambiguous.
So it will just reject the command?
It will reject it, or worse, it'll try to guess and send it to the wrong one.
So what is the solution?
You must use a fully specified route.
Yeah.
You have to tell the router, send this packet out of serial 00 and send it to the neighbor FE80.1. By tying that generic address to a specific interface, you resolve the ambiguity.
That is a gotcha that I bet trips up a lot of people moving from V4 to V6.
It definitely does. In IPv4, next hop IPs are usually unique. In IPv6 link local, they are reused constantly. You have to be specific.
All right, we have covered a ton of ground. We've gone from manual transmissions to sniper routes to floating backup plans. Let's do a quick recap. The source material has a great cheat sheet summary. I'll run through the scenario. You give me the rule.
Let's do it.
Okay, scenario 1. Standard Ethernet network connecting multiple routers.
Use the next hop IP. Don't use the exit interface only, or you'll trigger an ARP storm.
Scenario 2. Point-to-point serial link.
You can use exit interface only. It's efficient, and since it's a pipe, there's no ambiguity.
Scenario. You need a backup path that stays offline until the main line breaks.
Floating static route, set the administrative distance higher than 1like5 so it waits in reserve.
Okay. Scenario. Stub network with one way out.
Default route, the quad 0, paint 0.0.0.0.0.0.0, the funnel for all unknown traffic.
Last one. Scenario. Your IPv6 next hop is an FE80 address.
Fully specify. You need the interface plus the IP to identify which neighbor you're talking about.
This has been a really enlightening look at something that seems so basic, but is actually full of so much nuance.
It really is. And if I can leave you with one final thought, it's about that philosophy of networking we touched on at the start.
Go for it.
We live in this era of AI and massive automation. We want things to just work. And honestly, most of the time, dynamic routing is great for that. But there is a distinct power in the static route. When you type that command, you are stripping away the uncertainty. You aren't relying on a protocol to converge. You aren't relying on a neighbor to tell you the truth. You are defining reality for that packet.
The dictator.
The benevolent dictator. There is no substitute for the absolute certainty and security of a manually configured path. Sometimes the administrator really does know best. And knowing how to wield that control, knowing when to use the sniper route versus the funnel, that is what separates a user from a true engineer.
Defining reality for that packet. I love that. It's not just typing numbers, it's architecture. A huge thank you to everyone listening to this deep dive into static routing. We hope you feel a little more in control of your network today.
Happy routing.
We'll catch you on the next Deep Dive.